I thought we'd go through Newton's laws today because a lot of problems that people have with dynamics and forces um, can be helped with a thorough understanding of Newton's laws. Now, Newton, he sort of founded Newtonian mechanics, and in order to do so, he invented calculus. His Principia Mathematica, his book, actually reads like a modern calculus or physics textbook, because he basically founded both fields. And in order to sort of explain things, he had to become a teacher. He was basically had to teach the rest of the physicists, Newtonian mechanics. Before Newton, people were basically using something called Aristotelian physics or Aristotelian mechanics, which is based off of basically observations and hadn't really changed for thousands of years. Philosophers had just sort of sat on a hill and looked at things and been like, yeah, I think this is how things work. But they didn't really do any experiments. No one really did experiments till like Galileo. So the time between Aristotle and Galileo, there's a big time gap there. So so people were using Aristotelian physics, and you know what? A child or a teenager before taking physics understands Aristotelian physics. And in fact, students going through physics courses and aren't doing well, they're using Aristotelian physics. Aristotelian physics is what you sort of infer just from watching things. Right? So if you're watching things, you're sitting on your hill and you're watching things go by, you're like, so if that person pushes that cart moves. And if the cart is bigger and heavier, the push required is larger, or it takes them a longer time to get going. Aha, okay. So pushing equals motion. Right? Pushing equals motion. That should make sense to your Aristotelian brain. That's what you observe in your whole life. Pushing equals moving. If you don't push something, it doesn't move. Now, Newton's laws, and particularly his first one, is to attempt to address this. Like these aren't like postulates. These aren't necessarily rules. In fact, some physics textbooks don't like to use really Newton's laws. They prefer to list out postulates of Newtonian mechanics, because Newton's laws are written as teaching points. They're teaching points. Because he's trying to teach people. So everyone's thinking pushing equals moving. Pushing equals moving. Force equals motion. In French, force equals quantité du mouvement. But quantité du mouvement, actually, quantity of movement, sort of evolved into momentum. So force equals momentum. Momentum is mass times velocity. Well, in ancient times is mass times speed. How fast something's going, how heavy it is. Pushing equals that. But that is false in Newtonian mechanics. That is not true. So his first law is to address this misconception. He needs people to start with a blank slate so that he can really get into Newtonian mechanics, Newtonian physics. So his first law here, you can see it on screen here, a body remains at rest or in motion at a constant speed in a straight line unless it is acted upon by a force. That's a common paraphrase of that. Right? He's saying that if something's moving, it'll continue moving unless acted upon by a force. This means that moving and force are separate. You can have motion without force. If you remove all the forces and it was moving, it's still moving. Right? So obviously that hurt a lot of people's brains. What do you mean? What do you mean? Well, okay, maybe someone pushed it in the past. Maybe someone will push it to slow it down. But something can be moving if you remove all forces. Force and movement are not the same thing. There's no equal sign. There's no proportional sign. There is a roundabout relationship between the two, in the past or in the future. But in the moment, motion, like speed, velocity, is not directly related to force, to pushing. So if a body is at rest and there's no force, it's going to stay at rest. If it's moving at constant speed in a straight line or constant velocity, it's going to just keep on moving like that if there's no forces. This is sometimes also called the law of inertia or the concept of inertia. I as a teacher, I don't really like Newton's first law, and I never really referred to it because it's just a teaching point, and I use it as a teaching point. I also don't like the concept of inertia because there's no formula for inertia. I like formulas. Formulas are practical. Again, the concept of inertia is a teaching point. The concept of inertia is an object has a tendency to continue to do what it was doing. So if it was spinning, it's going to want to continue to spin. If it was going in a straight line in one direction, it's going to want to continue to go in a straight line in that direction. It's not going to want to change direction. It's not going to want to slow down. It's not going to want to speed up. If it was at rest, it's going to want to stay at rest. In order to change it, you need some sort of force on it. So in terms of tests and stuff, sometimes the question might be, okay, someone's driving a car at constant speed or constant velocity. The car hits something and they go flying through the windshield because they weren't wearing their seatbelt. Why did that happen? Maybe it's multiple choice, and one of the answers is Newton's first law, or the law of inertia, or the concept of inertia. Right? If there's nothing to keep, no seatbelt, nothing to keep the person with the car, no force, the seatbelt would exert a force on the person, then the person's just going to keep on doing what they were doing, which is moving at high speed. And they're just going to go flying. Similarly, a common question is, I'm traveling on a bus, and all of a sudden the bus stops suddenly, and everyone gets thrown forward. Why does that happen? Well, you could say, well, Newton's first law. Everyone was going at the bus, and everyone in it was going at a constant velocity. All of a sudden, the bus stopped, but if there isn't sufficient force on the people, if the people aren't holding on tightly, and the force between the person's hand and, let's say, the bars, if there's no force like that, then they're going to keep on moving. If the absence of force, they're just going to keep on moving. You can also imagine on ice, how fast you can glide. If you had perfectly friction-free ice, you could basically glide forever. And that's that concept. If you remove all forces, an object in motion is just going to stay in motion. It's just going to keep on going. And you know the difference between sliding on shoes and sliding on skates, right? Right. Slide on skates, you can actually turn, right? Because you actually have edges of the skates can dig into the ice to exert a force between you and the ice to allow you to change directions. If you're sliding on shoes, can you change direction? No. You're at the mercy. You're just going to keep on going in whatever direction you're going. You have no control over that. So all those concepts, that thought, that force is not necessarily connected to how fast something is going. Something can be moving without force, and in fact, if there's no force, it's just going to keep on moving. It's going to keep on doing whatever it's doing. That can be called Newton's first law. That can be called law of inertia, or the concept of inertia. So hopefully that makes more sense for you. It's just a teaching point, although sometimes it's posed as a question as if this is some lofty rule. But it's just a teaching point. It's something that will help you understand qualitatively what goes on, and qualitatively how to use forces. That force is not connected directly to velocity. That's an important distinction to make. You have to make that separation. In fact, let's do a force concept inventory test. Now, at universities, there is a sort of standardized research test to see how good students' understanding is. And honestly, this is a good little quiz for you. So I'll switch here to my tablet here. And so here's the question. So I throw a ball up into the air, and it's on its way up and it's left my hand. Draw the free body diagram, or the force diagram, which means draw the ball and draw an arrow and a labeled arrow and of all the forces that are on it. And this is, there's a couple different versions of it. Some people, force G, force of gravity. Maybe some people draw, well, it's going upwards. So force from the hand. And then force of gravity. Maybe it's just, well, it's on its way up, so maybe it's just force of hand. Okay, and so I'll give you a moment to think about this. Which do you think is the most correct? And obviously I'm ignoring air friction here. Okay, have you thought about which one seems the most correct to you? Most people would answer the center one. And in fact, people going into MIT for engineering, 60, 70, 80% of them going into the program will answer that one. So, okay, you're just as smart as everyone going to MIT. Isn't that great? MIT for engineering. Isn't that great? It's wrong, though. Right? It's left the hand. The hand is no longer in contact with the ball. How can there be a force from the hand? You're connecting it with, well, it is moving now, So because it is moving, there must be this force of hand on it. But that's that quantitative movement, quantity of movement. Quantity of movement is separate from force. So force may have been necessary to get it to move, but you have to look at the instant. Is there a pushing force in it? Well, if my hand isn't touching it, there's no pushing force. All we have is the force of gravity, and if we could add air friction on it as well, right? So again, this is where Newton's first law sort of helps create that distinction. Force, velocity, you have to separate them in your minds, or else you're going to suffer. You're going to have so much trouble with mechanics. Okay, let's get started with, I'll go back to Wikipedia here. Now let's go to the second law. Now, if you read the second law actually makes the first law redundant. Second law, here's what Wikipedia says. At any instant in time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently, the rate at which the body's momentum is changing with time. So basically, the net force on an object, on a body, on one object, not on every object everywhere. The net force on one object. And what is the net force? The net force is the sum of all forces on that object. So the net force, the sum of all forces on that one object, is equal to that object's acceleration times its mass. Mass times acceleration. So if we go back to my tablet here, and let's just go to a new window here. So that means here, there we go. Force net equals mass times acceleration. You could write force net as, force 1 plus force 2. It's just all the forces on that object. Force 3 is equal to that object's mass, that object's mass, not another object's mass, that object's mass, times that object's acceleration. Now, if acceleration is constant, I could write this. Well, technically, acceleration is the derivative, right? It's the derivative of velocity with respect to time. If it's constant, or if we're talking about average velocity, we could write this as the change in velocity over the change in time, right? So the sum of all the forces, and this is all vector quantities, is equal to the mass, which is a scalar quantity, times the change in velocity over the change in time. So if net force is 0, the sum of all the forces is 0, then the change in velocity is 0. The object either continues to move in a constant velocity, or if it was at rest, it stays at rest. Basically, the velocity can't change. It can be moving. The velocity can be a number. If the velocity was 20 kilometers per hour north, and the velocity is still 20 kilometers per hour north, and it's not changing, then that means the net force is 0. The net force is 0, because net force is mass times change in velocity. Change in velocity. Net force is proportional to change in velocity. It's how the velocity is changing. So that's a very important concept, and this concept, which is in the second law, it's inside that formula. So it encompasses the first law, right? An object at rest will stay at rest unless there's a force on it. Well, yeah, if the net force is 0, if there's no forces, then the change in velocity is going to be 0. It's going to stay at rest, or it's going to continue moving in a straight line forever because there's no force. So I really hate the first law of Newtonian mechanics. I think it's almost a waste of time. But it is a good teaching point to separate out force from velocity. But I love talking about the second law better because it's formal. We can talk about it with numbers. We can actually have some vectors and we can do questions with it. It's so much more useful to point at and discuss. And there's not much more to it. You do have to be very, very careful because I see a lot of people confused when, a lot of people, they're trying to follow something on the board, and they easily get lost. And when they're trying to do their homework, and I see they're just taking all the forces in the question, they're just putting into FNet. And then sometimes they get the correct answer, and sometimes they don't. And they're like, why? I don't understand. I did what he did on the board. He took a whole bunch of forces and he put it all into FNet, and why isn't it working? Well, it's a sum of forces on one object. If you have two objects, then each one should be treated separately. Sum of the forces on object A equals the mass of object A times the acceleration of object A. Sum of the forces on object B equals the mass of object B times the acceleration of object B. Now, if both objects are stuck together, we could treat it as a big object. Like for my body, I don't have to be like, well, technically every cell in my body is a separate object with mass. Every atom has its own mass. Do I need to break up my body into individual atoms? Well, no, I can treat it. It's all moving to. I used to teach a class on biomechanics, and yes, we could talk about like an elbow and different joints, but let's say I'm on a skateboard, I'm on a bicycle, I'm on a bus. You could treat the body as just one object, one like ball. Um, so let's say an object A and object B, and they are stuck together, then yes, we could do the sum of the forces on this new object, A plus B, equals to the mass A plus B times the acceleration. Remember, they're stuck together, so they have the same acceleration, the acceleration of A and B together, because they're stuck together. There are a couple tricky questions involving two objects colliding, maybe a conservation of momentum, conservation of energy question, or again, unlikely to have conservation of energy unless it's an elastic collision. But if they're stuck together, it's an inelastic collision. If we're talking about momentum, you might not have covered momentum yet. So anyway, we have objects colliding together, and let's say they move together, and you could talk about the force during the collision and things like that. So it's important to think about, well, if they're moving separately, they have different accelerations, we have to treat them as different objects. If they are stuck together, it may be more useful to think of them as just one object with everything stuck together. Now, when and this is interesting, when I went to do my PhD, I talked to other people from around the world about their undergraduate educations. And when I was a teacher, I talked to other physics teachers about, what did you do in studying? People who succeed, what do you do? I succeeded. Did you do what I did? And almost everyone did what I did. Physics turns out to be one of the simplest courses, one of the easiest courses, because the number of formulas is actually much less than math. The number of postulates, the number of rules is much, much less than math or chemistry. You actually have very few rules, but the rules, you have to thoroughly understand the rules. Right? It isn't just F equals ma, you put in any acceleration, any force. It's the F net on one object equals that object's mass times that object's acceleration. And here's what people who succeeded did. They would create a formula sheet, and they would write out all of the meanings of each of the symbols. Not just F equals force. F is the net force on that object, to make it clear for themselves. Now, a lot of teachers learn sort of the wrong lesson from this, because I see a lot of teachers try to get their students to learn this way by, okay, I'm going to let you make your own formula sheet, hoping that the students are actually going to go through the book and read the formulas. But the problem with that is that formula sheet will then have all that extra information stripped off. Oh yeah, we're not allowed to put explanations on the formula sheet. It's important to make a cheat sheet not to bring with you to the test, but you make a cheat sheet just for the fact of learning. It's a learning exercise. It's something to study the night before, the day of. I don't want to be confused about what a symbol means. It's so silly. I taught physics for so many years, and after an exam, let's say it was an exam on momentum. Momentum is typically P equals mass times velocity, mv. I'd ask people, okay, what does the P stand for? And the student would be like, this is after the exam where they failed. The position, P for position, that makes sense to me. What does the M stand for? Momentum? It's no wonder they got like 10% or 20% on the test. But I did every question in the book. And literally, there's one girl who did every single question in the textbook. And how could you do every single question in the textbook and still get like 15%? It's because you're just sort of copying patterns. You're just sort of testing things out. Okay, I'll take these forces. Okay, that didn't work. Maybe if I leave this force out. So she was just answering all the questions about trial and error. So she wasn't really learning. She wasn't understanding. When you understand physics, when you understand the concepts, you'll be able to do the questions in the back of the book or the end of the chapter without actually writing them out. You'll know you have it right. You'll know you'll have done it right without having to get out your calculator. You'll be like, okay, I understand. This is just like that question before. Now, even for myself, I sometimes don't know if I understand a question. Sometimes I do. I'm like, yeah, I know how to do this, and I know how to do this, I know how to do this. But I'm like, wow, that looks really complicated. I'm not sure if I know how to do that. I should work on that. And then halfway through, I'm like, oh, this question 8 is just basically a question of what question 1 and 2 sort of combined. It's just multiple parts. I get it now. And that skill will allow you to study so much faster. So I know I'm getting a lot into study skills, and it also starts with this formula. So many students don't understand this formula. That's net force and the mass of that object and that object's acceleration. And that is sort of the core of their problem, why they can't pass any tests, is they just don't understand the formula. Now, one other thing to talk about the formula is the formula is a vector formula. And while you could do vectors with vector notation, I hat, j hat, things like that, it gets really, really messy. You should have already done kinematics, or typically you do kinematics, v final equals v initial plus at, right? You would have already done that probably already. Hopefully you've done two-dimensional kinematics. But anyway, it's important that to do math with vectors. Typically what you do is you take your problem and you break it up into x and y. Now it helps if these vectors are perpendicular to each other. Technically they don't have to be, but it helps. And technically they don't have to be, let's say x doesn't necessarily have to follow the horizon, y doesn't necessarily have to be up and down. Sometimes in a question, let's say it's one of those pulley questions with a mass and a rope and a mass or something, it might be beneficial to do xy like this. And you could have a different xy for both objects. That's possible. But what's important is if I'm going to do a calculation involving vectors, I need to have an x and a y. So let's say I'm doing a calculation for that object. I need to have an x and a y. And then I need to break all my vectors into components. Right? So in this question, I'll have force of gravity. Now, force of gravity, the way I have this the way I have this written is force of gravity in this axis is going to have a positive x component and a negative y component. Maybe if I had used a different one, if I had used, it's getting behind my head here, if I had used a more standard xy, then this force of gravity would just have a negative y component and no x component. Both ways will give me the correct answer. Both ways will give you the correct answer. You can use both. You don't want to go back and forth between the two like halfway through the problem. You want to be consistent. But both. So if you're following examples with your teacher in different textbooks online, you may see them use, let's say an angled one, because sometimes it makes some of these inclined plane questions much simpler to use an angled one. It might be, well, why does gravity have an x and y component all of a sudden? Well, because they're using an x and y that's sort of tilted. So anyway, you have to break everything into x and y components, and then you can use these formulas like the F net equals ma. You can do F net x components equals the mass times a x components. And then you can just do your basic math. Remember, the plus and minus signs matter. Plus in the positive x direction, negative in the negative x direction. Remember that net. It's not just one force or the force on multiple objects, it's a net force of, so the sum of all the forces, F1x, F2x, F3x, change in velocity x, right? And then you would do the same thing for y. And then let's say you want the final answer to be the magnitude of a vector. Well, if you want the magnitude of a vector, you have to take, it's the square root of the x component, let's say f net x squared plus fy squared net. And that'll give you the magnitude of the final. So I'm just a sort of a quick review of the sort of components and just sort of vector physics and vector math. Here, vector math is really what I just did an overview of. Okay, we have one law left to quickly talk about. So let's go back to display here. We have Newton's third law. If two bodies exert forces on each other, these forces have the same magnitude but opposite directions. For every force, there's an equal and opposite force. Right? How many times have you heard that used in common parlance, common language? It's a common saying. It's often used for emotions and relationships, and Newton was obviously talking about physics. For every force, there's an equal and opposite force. Now, some people would think, well, wait a second, if there's equal and opposite forces and I add up vectors, aren't they going to cancel each other out? One's in the positive direction, one's in the negative direction, plus minus is going to give zero. Well, they're on different objects. If there's two objects interacting, object A and object B, Well, the force of A on B is going to be equal to the force of B on A. They're in different formulas. They're in different F nets. F net for object A and F net for object B. So they're equal and opposite, but because they're in different formulas, you do different math with them. That's why they don't cancel out. And it's sort of a hard concept to sometimes wrap your head around if you haven't fully understood laws 1 and 2. Remember, force is related to change in velocity, and it's not just any force, it's the net force. The third law is just talking about one force. Acceleration, the change in velocity, has to do with the net force. So I would do an experiment with my students. I would have 4 sensors. I had one student hold one force sensor here, another student hold a force sensor here, and they'd basically push them together. And these students would be shoving each other back and forth. Okay, push me backwards. Now push me backwards. Okay, push at constant speed. And guess what? The force sensors would read the same thing all the time. It doesn't matter. Now, if you were accelerating in one direction or slowing down, which would be a deceleration, slowing down is an acceleration opposite the velocity vector. So whether you're speeding up or slowing down, whether your velocity is changing or not, those forces, A on B and B on A, were the same magnitude but in opposite directions. But what changes is the net force. If the net force is in one direction, then you're going to speed up in that direction. If the net force is in the other direction, then you're either going to slow down or you're going to speed up in this direction. So it's the net force that governs whether something's going to accelerate or decelerate, speed up, slow down. And it's this A on B and B on A has more to, it's important because it does tell you interactions between objects. If you have a question like my pulley example, I had drawn 2 boxes there. I have two free body diagrams. And so you might have 2 or 3 objects interacting to each other, pushing on each other. Let's say a person pushing a box. If you want to fully understand what's going on in that problem, in order to solve the math, you may have to use the fact that the magnitude of those forces are the same. In those formulas, you can say, FA on B, let's say, is X. You're unknown. FAB and FBA are the same number. Then they're the same variable in your formulas. You can substitute. You can isolate for one and substitute it into the formula. So the Newton's third law is important to understand for the interaction between objects and for solving multi-body problems. And remember, so it's not it's even important. Let's say I'm leaning against the wall. Right? So I'm pushing the wall. So if I'm really heavy and the wall is very weak, I might break the wall, right? But the wall, I would fall over if the wall wasn't pushing on me. So it's important to realize when things are in contact, if there is a pushing, then the pushing happens on both sides. If there's a rope and I'm pulling on a rope, not only is it lifting me up, let's say it's attached to the ceiling, not only is it lifting me up, but I'm also pulling on the rope and I might break the ceiling, right? So you have to remember that there is forces on different objects. You can't escape that. You can't have a force without a force on the other object. You can't push something without being pushed back. And so that's important in engineering. You don't want to forget that. You have to account for things like that. Anyway, so this was very quickly going through Newton's 3 laws of motion, Newton's laws. Hopefully, I tried to come up with a slightly different angle and put in some study tips for you. I wish you all the best. Cheers.